Okay, let's dive right in. Hidden inside almost every single piece of electronics you own is a secret language, one that's written in these little colored stripes. Today, we're going to crack the code on these tiny components, the resistors, and figure out exactly what they're trying to tell us. If you've ever peeked inside a phone, a computer, or even your TV remote, you've definitely seen them, dozens of these little guys wrapped in colored bands. They kind of look like secret messages, don't they? And in a way, they are. But by the end of this, you'll be able to read them like a pro.
Visit youtube.com/avidsystem and don't forget to subscribe.
So you might be wondering, why not just print the value right on them? Well, the simple answer is they're just too darn small. I mean, imagine trying to read a number like 4,700,000 on something the size of a grain of rice. It'd be practically impossible for us, let alone for the automated machines that make millions of these things. A much more elegant solution was needed. And that solution is the resistor color code. It's this absolutely brilliant, internationally standardized system that packs all the critical info you need into a series of simple, high-contrast colored bands. It's a universal language for engineers, technicians, and hobbyists all over the world. All right, so how do we learn this language? Well, every code needs a key, right? And for us, that key is the color decoder chart. This is where we're going to translate those colors into actual usable numbers. Now, before we even look at the chart, here's a handy little trick to remember the color order. It's a classic mnemonic: bad beer rots our young guts, but vodka goes well. The first letter of each of those words gives you the color, from black and brown all the way down to white. It's a little silly, I know, but trust me, it works. And here it is, the decoder ring itself. As you can see, each color from our little phrase corresponds to a number, 0 through 9. Now, what's really interesting here, and this is the real genius of the system, is that third column, the multiplier. This tells us how many zeros to tack onto the end, and it's the key to reading massive resistance values in just a fraction of a second. Okay, let's put this into practice. We'll start with the most common type you'll find pretty much anywhere, the 4-band resistor. Once you master this one, the others are going to be a piece of cake. Reading a 4-band resistor is a simple 4-step process. The first 2 bands, they give us the first 2 digits of our number. That third band is that all-important multiplier. And the fourth band, that tells us the component's precision, or what we call its tolerance. Theory is great, but let's get our hands dirty with a real-world example. So imagine you're holding a resistor with these 4 bands: brown, green, red, and gold. Let's see how this builds step by step. First up, we look at the first band. It's brown. We check our chart, and we see that brown corresponds to the number 1. Simple enough, right? That's our first digit. Next up is the second band, green. Back to our chart, and green gives us the number 5. So if we put our first 2 digits together, we now have the number 15. Now for the magic, the third band, the multiplier. In our example, it's red. The chart tells us that red means multiply by 100. So we take our number, 15, and we're going to multiply it by 100. And that gives us our final resistance value, 1,500 ohms. Ohms, by the way, are just the unit we use to measure electrical resistance. We can also write this as 1.5 kilo ohms or 1.5 k ohms. See? It's brilliantly fast once you know the code. But hang on, what about that last gold band? That's the tolerance. Gold means this resistor's actual value is guaranteed to be within plus or minus 5% of that 1,500 ohms. This is super important for knowing exactly how precise your circuit is going to be. Great! You've just mastered the 4-band code. And the good news is, you've already done the hard part. The 5- and 6-band resistors you see in more advanced electronics, they're just a simple extension of this exact same system. So why have different types? Well, it all boils down to precision. 4-band resistors are the workhorses for everyday electronics. But for super sensitive stuff like medical equipment or scientific instruments, you need the higher precision offered by 5- and 6-band resistors. The only real difference in a 5-band resistor is that it adds a third significant digit before you get to the multiplier. So instead of a 2-digit number like 15, you might get a 3-digit number like 152, which allows for much more specific, precise values. The multiplier and tolerance bands just shift one spot to the right. It's really that simple. And that mysterious 6th band? That's for really high-performance gear. It specifies something called the temperature coefficient. In simple terms, it tells an engineer how much the resistor's value will drift as the device heats up or cools down, something that's incredibly important in things like professional audio or even aerospace technology. Okay, so we've cracked the code, but let's just zoom out for a second and ask the bigger question: why is this simple system of colors so important? The power is all in its standardization. It's a language that a technician in Tokyo, a designer in Berlin, and a hobbyist in Brazil can all understand instantly. It packs a huge amount of data onto a teeny tiny surface. It can be read by machines at lightning speed, and unlike ink, the colors won't easily wear off. So the crucial point is this: the resistor color code isn't just some clever trick. It's a quiet, foundational piece of engineering genius. It's one of those simple, elegant standards that allows for the complex, global, and automated manufacturing of the technology we all rely on every single day. It really makes you wonder, doesn't it? The next time you look at a circuit board, you won't just see components. You'll see a language. So what other hidden languages, what other elegant systems are hiding in plain sight in the technology that's all around us?
Thanks for watching.